Since from the last time.
I have one question.
Huh?
I have one question.
Yeah.
From the tensor representation. Tensor representations are always given in terms of fundamental representation in the algebra, because here they specify that if you have a algebra whose fundamental representation is of some dimension r, then the tensor representation will be t, I1, I2, I3, where the i's go from 1 to r. Specifically to r.
Sorry, repeat that again.
And if I have a fundamental representation of dimension r, then we can consider tensors of the
Tensor. Okay.
Well, this r could be any number. If I consider another representation of this Lie algebra, for example, for SU2, I can consider SO3, and this could be, for example, a rank 2 tensor matrix 3 by 3. Right. Is this still a tensor representation of SU2 or some another tensor representation?
I mean, you see, tensor, okay, it's just one way of doing it, right? Anyway, there's not even a reducible representation, right? Tensor, once you have this tensor, then you have to, again, decompose in terms of irreducible representations by looking at the symmetry group, right? There's just one way of doing it. For SO3, for example, what you would do is you will again write them tensors, but the indices will be vectors, no? The standard, like SO3 is a rotation in some d-dimensional vector space. So the standard tensors that you have, like metric tensor, all of these things, the indices go from 1 to the dimension of the space, right? Okay, that's just, sure, that's tensor. Tensors are there, but they're not irreducible representations, right? I think the best way to classify the irreducible representations are given by giving the highest weight. Actually, I am following a bit different from the notes. Actually, quite different from the notes. In fact, maybe next year I should rewrite these chapters to. You can ignore these notes a little bit. Although what is written in the notes is correct, but my focus is a bit different. So I'm trying to class representations, irreducible representations, are given by highest weight. This is, I think, the most important point I'm trying to stress actually in this course. The highest weights are given by specifying the highest weight. Highest weight. Did I turn it on? Yeah, it's okay. Highest weight. Just like in the SU2 case, we saw how do you specify the representation? By specifying the spin, right? Spin G. So the highest weight there in the SU2 case was the state which was annihilated which satisfied such that J plus acting on, or sigma plus acting on the state on the highest weight is equal to 0. Right, that's a definition. So you decide, so here in SU2 case, we said, okay, this is a raising operator, right? And then we said the state which is annihilated by the raising operator, that's the highest weight. And once you have that, once you have this state, highest weight state, then you start applying E minuses, right? And keep coming down. And that way you get a complete irreducible representation, right? The same thing that what I was trying to show is that for all of this, for SU3 also, this works. Huh? The idea again is to decompose, to choose your, what is the analogs of the raising operators. But now it's a bit more complicated because there are several SU2s. No, so we said. So we looked at these two SU2s. I think what were we calling last time? Alpha 1 and alpha 2, right? So the roots were the following. We discussed the roots, which was like here. Okay, this is in the. So this was what we were calling alpha 1, alpha 2, alpha 3. Oh, no, I think this was what I was calling alpha 3, alpha 2, and the minus alpha 1s. Right?
Can you start recording?
Yeah, it is. I think it's on. Yeah. It's on. Yeah. Okay. So now one of the things that we notice is that x alpha 1 with x alpha 2 commutator, if I look at these two, right, this gave rise to some number times x alpha 3. Right? So, and furthermore, we also notice that for every non-zero root, there is an SU2. Right? So for alpha 1, we have the x alpha 1, x minus alpha 1, and some combination of the kata, which is we were calling H1. This formed one SU2 algebra, and similarly x alpha 2, x minus alpha 2, and H2 formed another SU2 subalgebra. And if you wish, you can also choose x alpha 3, x minus alpha 3, and some other combination, which is of course some linear combination. I think it was H1 plus H2. Anyway, I'm not sure about that. Some combination of H1 and H2, which formed another SU2. Okay. So now we use our knowledge of SU2. So what we do is we try to find the highest weights of this SU2 and that SU2 and that SU2. But the point is that this SU2 I can obtain from here, you see, because of the fact that x alpha 1, x alpha 2 is proportional to x alpha 3. So it is sufficient to just specify the state which is annihilated by x alpha 1 and x alpha 2. Right? That will be automatically annihilated by x alpha 3. Right? So this is the idea. So we use these two SU2s and in particular look at the highest weight simultaneous, which is highest weight simultaneously for both SU2s. And then we start constructing all the representations, the entire irreducible representation. I don't know which examples I think I gave you the fundamental representation, right? But yeah, we can also do other things. And so what is the idea then? So we say that the highest weight for SU3, highest weight for SU3 will satisfy x alpha 1 acting on the highest weight, HW is a short form for the highest weight, equal to 0, and R x alpha 2 for SU3, x alpha 2 HW is equal to 0. Right? And then furthermore, we can specify, just like for the SU2 case, we found this highest weight, and then we could also, since we could also always diagonalize R sigma 3, right? So we also have the eigenvalue of the highest weight, which was 2j, right? In the spin j representation. This is sigma 3, not sigma 3 by 2. For sigma 3 by 2, it would be j, but I just multiplied by 2 because that's the convention we are following here. So from the convention of SU2, just multiply by 2. So 2j is always an integer, you see. J was a half integer, so 2j is 2 times j is always an integer. So that's an integer. And then once you specify that, then you get the spin j representation here. Now here what I do, I have two quantum numbers, RH1 and RH2 on this highest weight. Right? This will be some numbers. Let me call it N1 times the highest weight, and this acting on the highest weight equal to N2 times highest weight. Right? Because I can simultaneously diagonalize them. Right? So I look at this diagonal basis and ask the question and specify some highest weight. Right? So now you see, as opposed to in the SU2 case, we had just one integer which specified the entire irreducible representation. Here I have to specify two integers, N1 and N2. Okay. So irreducible representations of SU3 are specified by specifying two integers N1 and N2. These integers are non-negative. So N1 and N2 are non-negative integers. See, they cannot be negative, just like here. This cannot be negative, right? Because we are looking at the raising operator here. Right? If we had used lowering operator, sigma minus, then this would be necessarily, this will not be 2j, it will be minus 2j. Correct? But since we are talking about the raising operator is something which increases increases this quantum number, right? Lowering would decrease the quantum number. So when you say highest weight, that means it cannot increase further, right? Because if I apply the raising operator here, that annihilates it. So in that representation, there's a maximum, highest value, right? So that's why it's non-negative. If it is 0, it would be singlet. I mean, it's a one-dimensional representation. If it is if this is equal to 1, it is spin half representation, so doublet, right? In SU2. The same thing. So we are using the SU2, knowledge of SU2, to get this information, to use this labeling system. Now, once you have that, then we can start constructing all the other states, right? Just like in SU2 case, from there we started applying lowering operator to get all the other states in that representation. And the same thing we try to do here. So let's just try, so I think, I'm not sure what examples I did. I think I gave you the fundamental representation. Okay, so let's start. So in this label, in this basis, I mean in this language, what is the adjoint representation itself? You see, for adjoint representation, you had, look at this alpha 3, right? So what is the highest weight here? Huh? So if you look at the adjoint representation, so what are we looking at? We want to ask adjoint of x1, x alpha 1, acting on something, on one of these objects, is equal to 0, and add x alpha 2 acting on that's on the same state is equal to 0. So which one is it? Remember, the roots add up when you take the commutator, right? After all, this just means commutator, right? Adjoint is a commutator. Roots add up. Eigenvalues add up, right? I mean, like here, you see, if I started with some state Jm and apply R sigma plus, it will have an eigen. Now I ask the question: what is the eigenvalue with respect to R sigma 3 for this state? It will be n plus 1, right? Because this has eigenvalue plus 1, this has eigenvalue n. So it will become additive. The same thing here is going to become additive. Eigenvalues will just add up. So now, if you look at, these are the eigenvalues after all in the adjoint representation, right? So whatever we are doing, we are just add whatever the state had, so eigenvalues. I'm just adding this eigen root alpha 1 and alpha 2 to that. So which will be annihilated? It's clear alpha 3 will be annihilated, because if I add alpha 3 and alpha 1, I'm going to get some point here, but this did not exist in the representation, right?
What do you mean by alpha 3? Because alpha 3 is just an eigenvalue.
I mean x alpha 3, no? So this x alpha 3, acting on x alpha 3. Alpha 3 is eigenvalue. Just like here, m is eigenvalue, but now we are talking about the state which carries the, yeah. So alpha 3, so this is the state which is, this is the object which is carrying the alpha 3 eigenvalue.
No, we can say that in the adjoint representation, the states are actually themselves, the
Exactly.
elements of the algebra.
That's what it's like. Yeah. So yeah, joint representation is that way special, because it's acting on the algebra, on the vector space of the Lie algebra itself. So that's a bit special. So we want to look at just this. So, I mean, whatever the state is, I mean, if this was not 0, it would be something which will have an eigenvalue alpha 1 plus alpha 3, right? But that doesn't exist. So therefore, we conclude that it must be 0. Same thing with the alpha 2 plus alpha 3 would be something here. So you add these two vectors, there's going to be something here, and that doesn't exist, right? So alpha 3 is the highest weight state. X alpha 3 is the highest weight state of the adjoint representation. With this choice, I mean, I've chosen this to be, I've called them, as I told you already, that there is a lot of ambiguity because there are several SU2s now, right? I could have called this one as raising and that one as raising, for example. You know? So, but you choose, once you make your definition that this is my raising, these are my raising operators, then with this definition, alpha 3 is the highest weight state. If I had chosen, for example, this one and this one as my raising operator, right? then this would be the highest weight. Okay, so it depends. It's just a matter of relabeling. The different choices of raising the definition of raising operators. It's just a matter of reordering the things. It's not. You will get the same representation. It is not a different representation. Okay, so with this choice, I get that. Now, what are the eigenvalues? So, I mean, what are these numbers n1, n2, right? So, if you look at this here, with respect to this SU2, we have two SU2s now, right? Because I have chosen this and that as SU2. I have chosen these two SU2s. If you look at this, now when I apply the lowering operator, from here I will get alpha 3 minus alpha 1. So I apply the lowering operator. Raising operator annihilates it, so you don't get anything. So the only other thing I can do is apply the lowering operator, right? H1 of course gives an eigenvalue. H1 is an eigenfunction with respect to H1. So H1 acting on that will just give me a number times the same, right? So the only new state which I can create is by applying the lowering operator. And when I apply the lowering operator on here, I will get something whose eigenvalue is the sum of this and that, right? But the sum of these two is that. Okay. So add x minus alpha 1 acting on x alpha 3 is going to give me some number, non-zero number, times x alpha 2. Okay. This is non-zero. I mean, okay, but we will give a general proof of that statement when we discuss general Lie algebras. Huh? But here you can just explicitly work it out. You have the matrices for these, the 3 by 3 matrices. Take the commutator, and you will find that this number is not zero. Is that clear? I mean, this statement of additivity of the eigenvalues just tells you that whatever it is going to be some number times that, right? But it doesn't tell you whether this number is zero or not zero, right? So that, okay, that you have to, I mean, you can just check it by explicit the 3 by 3 matrices that you have. Just take the commutation relation and show that it is not zero. And that is it. You see, now if I apply further x minus alpha 1, then I'm going to, then I have to add these two vectors, right? Then I come somewhere here, and that doesn't exist. So, with respect to this SU2, this guy forms a doublet, right? Spin half. So this one carries a spin half with respect to this SU2. Spin half representation. What about this SU2? Again, raising operator acting on that annihilates it. But now I apply lowering operator, I'm going to come here. So again, and that's it. Then it stops there. So this is again a doublet. So the n1, n2 for this, for x alpha 3 in this notation will be n1, n2 will be both 1, 1. 1 because 2j is this quantum number is 2j, and j is half, spin half. So this is 1, 1. And one can explicitly check it. You can explicitly check it that h1, add h1 acting on x alpha 3, add h1 acting on x alpha 3 equal to plus 1 times x alpha 3, and add h2 acting on x alpha 3 is again x alpha plus 1 times x alpha 3. So those are the eigenvalues, right? n1 and n2. The numbers here were the n1 and n2 are the eigenvalues. Okay?
It is 1, 1.
1. It's exactly 1, 1. Yeah. Okay. So you can label. So the point I'm making is that you give me any number n1 and n2. These two numbers, two integers n1 and n2, and for each such non-negative integers, for each such choice, there exists an irreducible representation. Okay. Exactly like in the SU2 case. You give me any non-zero integer here, and there exists an irreducible representation. Okay. And exactly the analogous statement is here, this one, for SU3.
Can we choose an SU2 such that alpha 1 is the highest weight state?
For which?
For which alpha 1 is the highest weight state? If you choose, can you choose suggestion 3 such that alpha 1 is the highest weight state?
Alpha 1 is highest state for SU2. No, in this case, you are saying, can I choose two SU2s such that this is the highest value? Yeah, choose this one and this one. Take this and this as a raising operator.
So in this case, if we want to, calculate n, we will have to take the commutator of H1 with alpha 1, X alpha 1.
H1, not H1, because then the basis is different, right? If I choose this SU2 and that SU2, okay, this guy has H2, right?
Okay, so
that has H1 plus H2.
Okay.
So one has to use that to find the eigenvalues. And you will again find 1, 1 eigenvalue.
We have to do it with H2. Okay.
It should be, now I don't remember whether it was the third SU2, okay, for this was X alpha 1 plus minus alpha 1 with H1. This formed one SU2. X plus minus alpha 2 with H2 formed another. And the third one was X plus minus alpha 3. And I think it's just H1 plus H2. Huh?
Yeah.
Okay.
I was asking that because I remember that when you take commutator of H1 with X alpha 1, you get 2. So, but you said that it's going to be H1 plus H2. So for H2 it is minus 1. So
That's
one.
Yeah. It'll be again one. No matter whatever you choose, it will be always again. Okay. So let's. So we took. I think we took an example. The simplest example would be to just take the small numbers, right? Even for SU2, it's better to start with a small spin, right? Otherwise, the number of states is much larger in the representation. So let's start from the simplest one. One more thing I should mention here, that you remember for SU2, one of the important features of SU2 was that the multiplicity of the representation is the same. But not just that, I mean, of course, it also implies, but for every quantum number m, there was also a quantum number minus m in the same representation, right? So this is exactly what we are finding. Here it was 1, 1. So this is the quantum number with respect to the first SU2, and that's the second SU2. When I apply the lowering operator, nothing happens to that, right? Because, no, sorry, this also. So what is going to happen here? You're going to get minus 1 and 2, right? It's let me see how to say this. Because, I mean, H2 acting on, add H2 acting on X alpha 1 is not 0 actually. If you look at X alpha 1, add H1, H1 was this, 1 minus 1, 0, H1. H2 was, in our definition, it was 0, 1, minus 1, and 0. Right? X alpha 1 was 0, 1, 0, everything else 0. And this is X alpha 1. And X alpha 2 was 0, 0, 1, right? This was the alpha 1 and alpha 2, right? X alpha. And the X minus alpha 1 was 0 here, 1 there. I mean, transpose of this.
Yeah.
Alpha 3 would have been, X alpha 3 was 0, 0, 1, 0, 0, 0. So these were the three roots. Now, if you look at let's look at the commutation relation of add H1. So add H1 action is simply the commutation relation of H1 with X alpha 1. And what do we find here?
2 times X.
2 times X alpha 1, right? So 2 times X alpha 1. But H2, again, acting on X alpha 1 is minus 1. In fact, we have written down this 2a minus b formula and so on, right? Minus 1 times X alpha 1. So what it means is that when I apply X minus alpha 1, this means that the eigenvalues will be additive, right? You started with a 1, 1 eigenvalues of H1 and H2. when I apply x minus alpha 1, I will, I will get I have to subtract these eigenvalues with those eigenvalues, right? Because x minus alpha 1 will exactly the opposite, -2 and +1 eigenvalues. So this will become 1 minus 2, which is -1, but that will become 1 plus 1, which is 2, right? So this way I think you can probably chart out. So whereas here now what I will get is 2 comma -1. Here it will be -2 comma 1. So one can just write with just specify the eigenvalues, -1 -1, and finally here would be 1 minus 2, and then here is 0 0, right? The center. Okay, so now let me just erase this a bit because it's unreadable here now again. Let me just erase this. So we have here. Okay, this thing here. Alpha 1 minus alpha 1 minus alpha 2 minus alpha 2 alpha 2. Sorry, alpha 2 alpha 3. Okay. So I start from here, apply x minus alpha 1. So I make an arrow like this to show that I'm applying the lowering operator of alpha 1. I get here. Now if I apply another one, it should be 0 because it's a doublet, x minus alpha, with respect to this SU2. But by the time I have come here, now this is -1, 2, but when you look at this 2 is the H2, right? So both these numbers, this number 1 tells me that with respect to SU2, this should be a doublet, right? So when I apply x minus alpha 2, I'm going to come here. Okay, this 1 becomes -1, and then this 1, you have to add it up, right? Because, yeah, I mean, there's exactly the similar statement for x h2 x alpha 1 is -1, x alpha 1, and h2 with the x alpha 2 is 2. X alpha 2, right? So therefore you just again add it up. I mean the eigenvalues of this guy with the x minus alpha 2's eigenvalues. You add it up, you get that. Now this number here 2 tells me that this must be a singlet. Spin 1, triplet, with respect to this SU2, right? Because this number 2. The 2j is 2, so j is 1, right? So it's a spin 1 with respect to this, but indeed that is x alpha 2 itself. X alpha 2, the h2 and x minus alpha 2 gives you a spin 1 representation, right? A joint representation of SU2 is spin 1. So you start lowering this, lowering again x minus alpha 2. You come here, which will be h2, and again another x minus alpha 2. You get that. Same way here, if you look at this number tells me that with respect to this SU2, it's a spin 1 representation. So you come here with x minus alpha 1 and here x minus alpha 1. Because the spin 1, you have 2 steps. You can do 2 steps, right? Third step, of course, it will vanish because this is the lowest weight state then for the SU2. Okay. And then finally, if you look at this situation here, you see this number is 1 plus 1. So this is spin half representation with respect to this SU2. And therefore, you come here x minus alpha 1 and you get there. And similarly from here, you see this again as spin half representation with respect to the second SU2. So you can come back from there to this with x minus alpha 2. Right? So there are ways of going. So you start from the highest weight, start applying the lowering operators of these two guys, these two SU2s that we have picked out, right? So you come here, you go there. Now to come here, I have 2 possible ways. I can come like that and I can come like that. Okay? It is not guaranteed that, in general, these are 2 independent states. Whether you come like this or you come like that, there will be 2 independent states. And in this case we know, because this way of coming, I will get H2, right? Because first I came here, I went to x alpha 2, then apply the lowering operator x minus alpha 2, that is going to give me H2, because that's 1:2, right? Whereas this way of coming, I will get H1, because here is x alpha 1, apply x minus alpha 1, I'm going to get H1, right? So in this particular case, we know there are two linearly independent states that you get. But in general, it is not guaranteed. So that is something you need to check. So in this case, there are two states. So the multiplicity here is 2. I just write multiplicity 2. Here, of course, is 1, 1, 1, and 1. And then finally 1, 1. So that makes together altogether that's 8. That's an 8-dimensional representation.
Essentially, the multiplicity means the number of ways in which we can come from a higher straight to the
Yeah. Okay, sometimes there may be linearly dependent. And I will give you one example today. But generically, this will be linearly independent. But in some special cases, not for this representation, some other representations, it could happen that there are two ways of getting to some place or many ways of getting to some place, and not all of them are linearly independent. It could happen. Okay, so how did I conclude? In the adjoint representation, we know everything. But I said multiplicity here is 1. How? Because we know there must be a complete symmetry in the m quantum numbers. M and minus m must have the same multiplicity, right? If for any SU2, if I have an m quantum number, I mean, in some representation, spin J representation, then for each plus m eigenvalue, there must be equal number of minus m eigenvalue, right? That is just comes from the knowledge of SU2 representation. So I know that since I know there is one multiplicity here, here also is going to be multiplicity 1. Okay. Same way, since I know multiplicity here is 1, there must be also only 1. Because a priori, you see, to come here by this kind of routes of this ladder, I mean this kind of a thing, the one way to come here is this, this, this. Another way to come here is this, this, this. So a priori, there are two independent ways of arriving there.
But right? There's multiplicity 1.
Exactly. But it should be multiplicity 1. So you see, either way, whether you come this way, you get H1 here. This way, you get H2 here. But once you apply x minus alpha 2 on H1 or H2, I'm going to get some number times x minus alpha 2. Not some new, different state. Right? X minus alpha 2 is what you will get. Same thing here. Here also there are perhaps many ways of coming here. 1, 2, 3, like this, or like that. Now, there are many ways of arriving here, but it has to be multiplicity 1 again. This and this must have the same multiplicity. Or this and this must have the same multiplicity because it's a doublet. So each one of these guys have multiplicity 1, and this has multiplicity 2. So just by counting the number of ways is not good. I mean, one can get wrong answers. No? So because there are a lot of dependencies, they're not linearly independent in general. Okay, so this is, now let's take the other example, the fundamental representation, which is the simplest one. So we said any n1, n2, any choice of n1, n2, I should find the irreducible representation. Okay. So choose the simplest one, 1, 0. That's the simplest, the smallest one.
So what was the question that you were answering?
Sorry?
What are you answering? What was the original question?
What was the question, in fact? What was your question? What was it?
No, I think that his.
Yes. No, I think I started going from there. And I mean, that was about SU2, the tensors and so on. No? Tensors, you can also do it here. That's not the problem. I mean, you can, that has more to do with the tensor product representations. No? Tensor product representations. Where, for example, for the SU2 case, what we said, we take doublets, several tensor product of doublets. Doublet is the, so suppose there are k of them. Then I can think of it as some kind of a tensor, I1 up to ik. Where each of these indices go from 1 and 2. Each of the I goes from 1 and 2. Because it's a two-dimensional representation. No? So this can have only two states. So this is just corresponds to that. And then we already, I think, showed it, right? And, last week, that you can start considering various, for example, if I take any pair and symmetrize it, so let's say I1, I2, and symmetrize, so take I1, I2, and do nothing to the other guys. Yeah? Then this itself, this will not mix with the other possibility. It will always come back symmetric or anti-symmetric, symmetric or anti-symmetric, right? So that tells you that then you can already start decomposing this into smaller representation. This big thing, which is how many 2 to the power of k states are there, because each index has 2 possibilities, and there are k such indices. There are 2 to the k possibilities here. But this is a big representation which is not irreducible. That is simply because this is an invariant subspace, right? Because if I take the just symmetrize the first pair, right? This will never mix with something outside it. So this is an invariant subspace, right? So this big representation is reducible. Okay. And now you can start, but this is still not enough, because what about this? I3 have a I4. I mean, I can, let's say, take even 3 of them. This is not enough. You can talk about the fully symmetrized, or fully anti-symmetrized, or this take pairwise. I mean, that slightly more complicated combinations we wrote down, right? Where you symmetrize in the first 2, then anti-symmetrize the second in different orders and so on, right? But all of them are guaranteed to be irreducible, not invariant subspaces. No? So this is how you try to start doing this. But equivalently, what I'm trying to do is I'm not using that procedure, right? I'm just saying that, okay, take some highest weight state. I will come with an example now. I mean, in the tensor products, I will take tensor products. But let me just do this first for 1, 0. Because you want to see some representation, some irreducible representations first. SU2 case, we were lucky. We saw all of them in one shot. Spin J representations, right? We could construct all of them in one shot, right? Here it's much more complicated. So let me just construct a few of them. Then I will get back to this tensor products in the SU3 case. Some simple example. I'm not going to give all the general things, but some simple examples. So this is what is called the fundamental representation. So in this picture again, let me draw this. So I started with the so here and some these three SU2s. Okay. So 1, 0 will be some point here. Let's say some point here. This I call 1, 0. Now, given the fact it is 0, remember this is these are the eigenvalues of the H1 and H2, and of the highest weight state. So H2 equal to 0 means it's a singlet with respect to this SU2. This was alpha 1 and this was alpha 2. So, and these numbers are H1, H2. Was I calling H1, H2? I don't know. Yeah, whatever. H1, H2. Eigenvalues. Eigenvalues of H1 and H2. These numbers, 1, 0. Maybe I should call something else. Maybe M1 and M2. Eigenvalues. No, that's not correct. I should put here 2J1 and 2J2. Because indeed that is the highest weight. So it's 2J1, 2J2. So this tells me that J2 is 0. So a singlet, right? So x alpha 2, x minus alpha 2 when it acts, it doesn't take anywhere. It gives you 0, right? Because it's singlet, or the SU2. On the other hand, this tells me the number 1 here tells me that J1 is spin half, so it should be a doublet with respect to this SU2, right? So I apply this x minus alpha 1 on that. I mean, I'm omitting this R. This is in that representation. But I hope it will be understood that when I apply x minus alpha 1, it is in that representation. Okay. So when I apply here, I'm going to get something whose eigenvalues will be adding this eigenvalue to that. But this one was minus 2 comma 1. Right? This is what we were doing. maybe I should write it down somewhere. The eigenvalues of x minus alpha 1 was minus 2 comma 1. X minus alpha 2 with respect to h1 and h2. This was 1 comma minus 2. This is useful to remember. So when I apply x minus alpha 1, I'm going to get here minus 1, 1. Right? Just add this quantum number to that quantum number. You get that? And now, that's it. I mean, it cannot go further because this was a doublet, right? This was a spin half. There was nothing. This will be the lowest state of that SU2. It will stop there. But now, if you look at this second number, this is 1 plus 1. Okay. So that means it must be a doublet of this SU2. So I can apply x minus alpha 2, and I will come here. And now the quantum number of this is this plus that, which gives me 0, comma, minus 1. Right? And that's it. Just stop now. You cannot do anything because now this is 0. I mean, this was a doublet. So if I apply further, it gives you 0, right? This is a doublet with respect to this SU2 because of that number 1. So you get 1 and minus 1. But now what happens? So I cannot apply any more x minus alpha 2. What about x minus alpha 1? No, because this is 0, so it's a singlet of the SU2. Okay? So it just stops there. So that's a triplet representation. Altogether, I mean 3. A triplet of SU3, not SU2. This is a 3-dimensional representation of SU3. And that was a defining representation, actually. I mean, the way we defined H1 was 1, minus 1, 0, and H2, H1, that was a defining 3 by 3, and H2 was 0, 1, minus 1, 0, 0. So notice that this state 1, 0, eigenvalue 1 and this one, so this state in that, so writing it, this acting on a 3-dimensional vector, so this state was simply 1, 0, 0, right? That will just give me exactly the eigenvalues. Then if you take, so this one will be 0, 1, 0 in this basis, right? I mean, I choose these 3 bases. And the last one here is 0, minus 1, it is 0, 0. This notation is clear? I'm just writing down this precise eigens. I mean, this is my fundamental representation, right? H1 is a 3 by 3 matrix, H2 is 3 by 3. Now I ask for the eigenvalues of various states. So the 1, 0, 0 state has exactly these eigenvalues. 0, 0, 1, 0 state has these eigenvalues, and 0, 0, 1 state has these eigenvalues. So these are exactly the eigenvalues of the fundamental representation, of the defining representation. That is how we defined SU3, right?
We didn't call them the weights.
Yeah, these are the weights, exactly. These are the weights. So yeah, roots. Yeah, I mean, these are weights are just. I mean, roots are basically weights, but for the adjoint representation. But for generic irreducible representation or generic representation, you call the eigenvalues or the weights. Eigenvalues with respect to the Kaplan-Meier algebra. That's so. These are the weights. And then there is, of course, a complex conjugate representation. So here I started from 1, 0, but now I could have also started from 0, 1. You see, I could start from this. This is what we call 3 representation 3. But I could also start with the highest weight 0, 1. Right? That's another. I mean, we have to consider all possibilities of all non-negative integers, right? So the smallest ones are 1, 0 and 0, 1. And in 0, 1, what I will get? Again, if I draw this picture, so 0, 1 starts with something like this here, 0 because H1 is 0 here. And so this 0, 1. So it's a singlet with respect to this SU2, right? But it's a doublet with respect to this SU2, right? So I apply from here x minus alpha 2. This picture is probably not very good. Okay, something like this. I apply x minus alpha 2, and I'm going to get the eigenvalues, which was minus 2, so minus 1, 1. right? I just add the eigenvalue of x minus alpha 2 to that. I will get this. And now after I have arrived here, now I see that this becomes a doublet of this SU2 because this is A1, no? So I can apply x minus alpha 1. And I come here, somewhere here, and that is minus 1, comma 0. Okay. And that's it. It stops there. Because this was a doublet, so it cannot continue there. Right? And this is now a singlet with respect to the second SU2, so nothing happens with x minus alpha 2. So it stops here. So this is the three-dimensional representation again. But notice that these weights are exactly the minuses of those weights. Right? For 1, 0, you have a minus 1, 0. Minus 1, 1, you have 1, minus 1. And here you have 0, 1 and 0, minus 1. So this is just, doing a parity, no? Not a parity, just reflecting, not reflecting, but for every point you go to the negative of that. And that's that way you get. That is the complex conjugate representation, which is what we mentioned some time back. So that's why it's called 3 bar. Okay. Now you can just, for fun, you can start doing, for 1, 1 we already know, 1, 1 is the adjoint representation. Now let's take a 2, 0, just to get some feeling for this. So again I draw for 2, 0. So now I have again, so I will draw this again. So 1, 0 was this. So 2, 0 is just like double that distance somehow. So this is 2, 0. Okay. So again, this tells me that this is a singlet of second SU2. 0 tells me it's a singlet. This tells me it's a triplet. So spin 1. So I can apply 2 times the lowering operator. Right? So first time I apply lowering operator, I'm going to get somewhere here, which will be 0, comma 1. And then I apply second time, I'm going to get here minus 2, comma 2. Maybe I should write down somewhere here. X minus alpha 1 has eigenvalues minus 2, 1. And x minus alpha 2 has eigenvalues 1, minus 2. So you just have to add these eigenvalues whenever you apply on some state. Now, here, so this we obtained. We just took care of the SU alpha x alpha 1 SU2, that SU2, this SU2. No? Now here I didn't have to worry about x alpha 2 because it was a singlet. But here I have to worry about x alpha 2 because now you see this number is 1, so it's a doublet. Right? So I have to apply an x minus alpha 2, which will bring you somewhere here. The picture is not, I don't know. So this one somewhere here. So this is, I should put an arrow, x minus alpha 1, x minus alpha 1. Now here I apply x minus alpha 2. Okay. Now what are the numbers here, quantum numbers here? Well, I just have to add to this there. So you get here 1, minus 1, right? Okay, it stops. This SU2 I don't have to worry about because it stopped there, it's a doublet. Okay. Now here, let's look at this. This is a triplet because this number is 2. So it's a triplet. So I can apply it 2 times. So once I will get something like this here, x minus alpha 2, and then another time, x minus alpha 2 again. So minus 2, 2, now add it up. So you get here minus 2, so minus 1, comma 0. And here I'm going to get minus 3. Am I making some mistake? Please, no, 1, 0, 0 and minus 2. I might be making some mistakes. Please tell me if you find some. Okay, so now that's fine. So we have done this. We have taken care of the fact that this is a triplet. And now look here. So as we said, this SU2 will not act because this was a doublet, so it will not act. But here, this is a spin 1 with respect to that, a spin half with respect to that. So it's a doublet. So when you apply x minus alpha 1, you will exactly get the same quantum number. Okay. But Now, there are two ways of getting here. One way this, one way that. But these two cannot be linearly independent. Because remember, for the multiplicity of this state and that state must be equal. This one, there is only one way to get here. Right? So there is only one state here. So even though it looks like there are two states, but actually there is only one state. Meaning that these two states are not linearly independent. One of them is proportional to the other. So you get one here and here is one. This is again, then these numbers must match. Because they have, in the SU2, this SU2 triplet, the quantum number 2 and minus 2 must have the same multiplicity. So this gives you a 6-dimensional representation. 1, 2, 3, 4, 5, 6. So this gives you a 6-dimensional representation. Okay. Clearly this picture, just like this picture, was not symmetric. I mean, when you take the point to the negative of those points, you get a different picture, right? That was at this 3 bar. Same way, this picture is not invariant under this, this x going to minus x, x in eigenvalues in this plane, no? So you will get another picture which will be the 6 bar. Whose highest weight will be, you can see, this point will go up, so it becomes 0, 2. So the highest weight of this will be 0, 2. Whereas of this was 2, 0. So that gives you another representation, 6 bar. You can, if you can just play with this. I mean, try with the 0, 2. Just by looking at this with respect to two SU2s, whether it's a doublet, triplet, or singlet, and try to draw these arrows. And you should be able to convince yourself that again you get a 6-dimensional representation.
Can we say that in the case of the adjoint representation, 8 is equal to 8 bar?
There's no 8 bar because the same is if you take the minus of this, you get that. So it's the same. You don't get a different representation. This diagram is invariant under the what do you call? I mean, I don't know what is the word for that. It's not a reflection. The reflection is on one plane, no? This is
the origin.
Huh?
Reflection around the origin, I guess.
Yeah, reflection around the origin. But usually you say reflection around some plane. But yeah, okay, let's do that. So just reflection around the origin. So this picture is invariant under that. But this weight diagram is not. So this will give you another one. This will give you another one.
Again, why the multiplicity should be 1?
Because if you look at this SU2, this SU2, I mean this SU2, X alpha 2 SU2, this is a spin doublet, right? So on any irreducible representation of SU2, you know that the number of states for plus n quantum number must be the same as minus n quantum number, right? That is always the case. Now here I have a plus 1 quantum number. There is one state here. So this must be. This is that representation, SU2 representation, right? This must have the same number of states. If supposing it was 2, I mean supposing that these two states were independent, there were two states, then there is no pairing. I mean these two states, both of them have minus half quantum number with respect to of this SU2. Then I should be able to apply raising operators, right? But how is it possible that when I apply raising operator, I get the same state here? So it has to be the equal number. So these pictures have a lot of these symmetries, symmetries of this type that these multiplicities must be equal. This must be equal to that multiplicity, and this must be equal to that multiplicity, right? Now here I already know that there is only one way to get here, right? So there is one multiplicity, and once that is 1, this is 1, that is 1. So this way you can figure out.
So we can say that this at minus 1, 0, the states are 2, but they are dependent. We can say that.
The states are 2,
but they are dependent.
When they're dependent, that means one state is equal to some number times the state.
Because if you make this diagram by superposing 1, 0, and 1, 0, you get 8. So, but you are saying there are 6.
Yeah, in this representation there are, yeah. But I mean, yeah, I could take another example, which is not, for example, if I take 2, 1, that will be very difficult to draw. I mean, but I'm not going to write down everything there, but just to give a counter example of this. Well, we already have a counter example here, right? Here, I mean, there are 2 ways of getting, and indeed there are 2 independent states. Actually, generically, that is the case. I mean, generically, in some special cases that happens. So now let me give you an example of. I mean, here you see we didn't have to do anything because I know that this must be equal to that, the multiplicity. So therefore, must be linear. They're not linearly independent, these 2 states, right? But let's just do something where it is not obvious. It could have been something different. Right? So let's take, instead of 2, 0, let's take 3, 0. Let's take 3, 0.
More physically relevant because it represents very.
No. Baryons. Okay, I mean the baryons, I will. So baryons come in the 3 quarks put together. Yeah, okay, in some sense, yeah. But you see, when we talk about SU3, which SU3 we are talking about? If you're talking about a column group, not the color group, flavor group, you're talking about the flavor group. Yeah, in the flavor group, you'll have all sorts of representations then, I mean, yeah. Okay, so let's take the 3, 0. So now again, draw the picture. Okay. So 3, 0 will be now 2, 0, we already did that. So 3, 0, actually 3, 0 will be so 3, 0 is somewhere here. What are the quantum numbers? That is okay, 3, 0, fine. So I started with the 3, 0 here. 3, 0 is the quantum number H1 and H2. Okay, H1 and H2 quantum numbers. Now this is a J equal to 3 half, right? For the first SU2. Second SU2 it's a doublet, singlet. So x minus alpha 2 will not move you anywhere. Just stay here. But here now I have to go 4 steps, right? This is so there are 4 states, so 3 steps I need to go to, right? This is a spin 3 half. So first I apply 1x minus alpha 2. Actually, I don't know, maybe this picture is not very good. Yeah, let's see, let's apply this here. I think it comes here, let's see. So x minus alpha 1, so that makes it 1, comma 1, right? This was exactly the 1, comma 1. So it comes to the alpha 3, weight of the x alpha 3. Then I apply again another, so this is 1x minus alpha 1. Apply another x minus alpha 1. I will get so it will be, what is it, minus 1, comma 2, right? Which is again the other root, alpha 2 root. I mean, it has the same quantum numbers. It's not the root, I mean, it's a different representation. Then I go back here, one more, so I'll get here minus 3, 3, right? Yeah, minus 3, 3. Okay, now start doing this here. This is now, okay, with respect to the second SU2, this was a singlet, but now it's a doublet. Okay, so it will come down, x minus alpha 2, and that gives you x minus alpha 2. So it's 2, comma minus 1, right? 2, comma minus 1. And then it stops here because it's a doublet. Now here, this is a triplet. So I apply x minus alpha 1 and x minus alpha 1. Yeah, x minus alpha 1. So here you get 0, 0, and here you get 1 minus 2. 1 minus 2. Okay. Now this is a spin, again, the spin 3 half. So there will be 4 steps. So I come here, then here, then, am I doing something wrong? No. So 3 steps. So I come here, finally I come here, right? somewhere here. So this will be subtract. So x minus alpha 1, alpha 2, sorry, x minus alpha 2, x minus alpha 2. So you get here 2, comma 1, right? Minus 2, comma 1. And then from here I get once more. So I will get minus 1, minus 1. And then finally here it is 0, minus 3. And that's it, it stops here. And now here you see there are several ways. I mean, you could, so to get here, I mean, to get to this place, for example, I have, I mean, here you see the multiplicities. Let's count the multiplicities where we know what multiplicity is. Here it is 1, right? So here it's 1. There's only one way to get here. Here also there's one way to get here, and this has to be 1, so 1. Okay? This is again 1 because these two have, with respect to this SU2 must have the same multiplicity. So 1 here, because from here again, I mean this must have the same. This is a, this is a triplet as far as this is concerned. This SU2 is concerned. These numbers must be the same. This number must be the same as that number, and then this number must be the same as that. Problem is here. Here we don't know, right? Whether multiplicity is 1 or 2. Because 0, 0 upon reflection around the origin goes to 0, 0, right? So you can't conclude anything from that. So a priori there are two ways, right? Because I come here, right? Or come here, come here. So there are two ways of getting there. Question is, are they linearly independent or not? So let's just try to work it out. This, I can erase this part. Like it happened for the adjoint representation, you see. In the adjoint, this part is almost like the roots. I mean, if you just ignore this extremum, I mean these 3 points, this part is exactly the roots, right? I mean of the adjoint representation, because this was the 1, 1, minus 1, and there are two of the 0, 0, right? So there, for adjoint, these two are linearly independent. But now we are saying that, what about this representation here? Are there two of them or just one of them? That is that point clear? So let's look at the states. So the 0, 0 state I can get by starting from the highest weight, so starting from 3, 0, and applying 2x minus alpha 1s, x minus alpha 1 square. Again, I'm forgetting this r. It's understood that this is in that representation, right? Otherwise, more precisely, I should write like that. Okay, but I will drop this r. It's understood that it's in that representation. And then you have r x minus alpha 2, right? Okay, I'm just writing this line, but that is one way. Other way is first apply x minus alpha 1, then apply x minus alpha 2, and then apply x minus alpha 1. Yes, both ways you are arriving there. Question is now, are they independent? So if they are linearly dependent, they are not linearly independent, then there must exist. So if these two states are linearly dependent, then there must exist say integers a and b, I mean not integers, some numbers a and b, such that a times x minus alpha 2, x minus alpha 1 square acting on the highest weight. I will just write this instead of writing 3, 0, the highest weight, plus b times x minus alpha 1, x minus alpha 2, x minus alpha 1 should be equal to 0. Then I should be able to find some non-zero a and b such that this is true, right? If they are linearly dependent. If I cannot find any non-zero a and b which satisfies this equation, then that would mean that these two states are linearly independent. Okay. How much time? Okay. So let's see. So if this is suppose the state is, suppose I found A and B such that this state is 0. This combination is 0. Okay. That means if I apply a raising operator on this state, it should also be 0, right? So what we do is that we apply, let's apply this x, say for example x alpha 2, for example. Let's say I apply x alpha 2. This is a raising operator now, right, on this state. When you apply x alpha 2, you see here what is the picture here? I have two possible states here because there are two ways of getting here, right? I take some combination of them and apply x alpha 2, so I'm going to get back there, right? Here, of course, there's only one state. So when I apply x alpha 2 in this linear combination, I'm going to get that one state times some number, right? But that number better be 0 if this equation is true, right? So that's going to give some conditions. Okay. So if I apply x alpha 2 on this, what I will get? So I take the commutator of x alpha 2 with x minus alpha 2. So what I do, I apply x alpha 2 on this. X alpha 2 with x minus alpha 2 will be h2, right? And I know the eigenvalue of this h2 of this state, right? Is that clear? Okay. But when you see, I should do that. So let's apply x alpha 2 on this state. X minus alpha 2, x minus alpha 1, x minus alpha 1. I just wrote it as explicitly. So what I do, I use always, because this is a raising operator, right? If I can push this all the way up to 3, 0, up to this is the highest weight. If I step by step, I start pushing it to the other end. Right? When it comes all the way there, it's 0, of course, right? So the idea is to start pushing it in. But whenever you want to push something in, you use a commutation relation. This is a standard trick. Yeah? So when I use so I can write this as a commutator plus the other ordering, right? X minus alpha 2, x alpha 2, x minus alpha 1, x minus alpha 1, highest weight, right? I just added and subtracted the same thing. But this commutator is h2. Okay. Now h2 of this state we already know. h2 of this state is 2, right? So this gives me, so this is 2 on that state. This was that state, x minus alpha 1 square. Now here, again I try to push. So I can write the commutator of alpha 2 with minus alpha 1. But notice that this was alpha 2 and x minus alpha 1 is this. The commutator is 0 because there is in the adjoint representation, not here, in the adjoint representation. There was no root, right? I mean the commutator of x alpha 2 with x minus alpha 1 is 0. Because there was no root, which was alpha 2 minus alpha 1, there was no root like that. So this is 0. So I can just push it through and that eliminates it. Okay. So the answer is just 2. So you find that when you apply here, you get 2 times A. So the first term gives 2 times A times x minus alpha 1 square, acting on the highest weight state. Now what about the second term? Let's look at the second term. Now, again I'm applying x alpha 2, right? I apply x alpha 2. It commutes through x minus alpha 1. So it comes here directly and push it. Then I just get h2 here. But h2 on this state. h2 is acting on that state. But this state was this state here because I apply only x minus alpha 1 step. You see? What I'm saying is that when I do the same trick here, I'm going to get h2 at this position. Because you have to keep track of the position. They don't commute, these operators, no? So it's in the second position. That means it is acting on this state. Right? So that means that state. So its eigenvalue for this state is h2 equal to 1. Right? So the second term is going to give me plus b, 1 times b, x minus alpha 1 square. So you see there is a solution to this equation. B is equal to 0. So B equal to minus 2a. Of course, this is not, you should also check one more thing. You should also check, I mean, here we applied x alpha 2, right? We should also check x alpha 1. Because if this is 0, then x alpha 1 should also annihilate it. I mean, x alpha 1 active 1 should be 0, right? So you should also check, so please check. Actually, in fact, I will just give you the exercises problems here because I'm not following the same techniques. No? So those instead of doing those exercises, so I would say check two things. So great exercise. Check that this b equal to minus 2a, or maybe just check it for the check this statement for when you apply when you apply x minus x alpha 1 on this state, on this a x minus alpha 2 on the state 3-0 state. And if you have done correctly using the, then you should find again that of course this state is going to be proportional to, when you apply this, unfortunately I erased that. But see what it's going to do, it's going to remove one of the x minus alpha 1. So you're going to get something like x minus alpha 2, x minus alpha 1. Is whatever the state is, it will be some combination of a and b with some coefficients when you apply this. Acting on 3-0. This is what's going to be finally, right? But the exercise is to find these coefficients by systematically pushing this through, and using the computational relation again and again. And you should see that the combination that you get is again like 2a plus b. Where was it? The combination will be of the form 2a plus b. Okay. That combination will vanish for b equal to minus 2a. Okay. Check that. So this is one exercise. And the third, you see, if the state is 0, its norm should also be 0, right? It should be 0 norm state. So now you see that you have two states, right? So first of all, what's the norm? For the norm, what you have to take, you have to take the Hermitian conjugate and take the norm, right? Let's say assume that the initial state 3-0, the initial highest rate state has been normalized to 1. Okay. So let's suppose suppose the norm of 3-0 state has been normalized to 1, or something, some fixed number, doesn't matter. Huh? Okay. Then a norm of, for example, this state x minus. First of all, defining what is the norm. So suppose I'm looking at the first state, minus alpha 2, x minus alpha 1, x minus alpha 1 of acting on 3-0. So the norm of this state is defined by this and the dagger of that, right? But the dagger of these guys become plus alpha 2, plus alpha 1, etc. No? So it will become 3-0 and then x alpha 2, sorry, I have to change the order. When I take the dagger, x alpha 1, x alpha 1, x alpha 2. Okay? The dagger of this. And same way, the dagger of this will be in different order of these operators, right? So the idea is to so I have two states, right? So what is the idea here? To write down, so let me call it state 1. This is, let's call it the state 1, or let's call it psi 1, and this state is psi 2. Okay? This state, I mean, this is x minus 2, psi 1. I just give a name to it, and this is psi 2. Okay? Two states. Then what I can do is I can construct a 2x2 matrix, let's say, let's call it n matrix, where nij is nothing else but psi bar I with psi j, in a product between psi I bar and psi j. Psi I bar meaning the dagger, sorry. Let me just write it like that. So it is understood that's a dagger of psi I. So you compute this, so it will be 2x2 matrix because clearly I and j go from 1, 2, right? So you'll get some number, let's say, I don't know, x something, alpha, beta, gamma, delta, let's say, these numbers I find. For these two states, I find this number. So this is the, so the question that you need to check is the determinant of n 0 or not 0? You see, if these two states were linearly independent, this determinant cannot be 0, right? Because but if the states are linearly dependent, then the determinant must be 0. So you should check. So the second exercise is to compute this and show that the determinant of n is 0. Okay? Show the determinant n is 0. Techniques will be essentially the same, because you see, once you have this kind of, suppose I want to compute this term, I have to compute 4 terms, right? So in particular, this is like n11. Yeah, this is like a computation of n11, right? So what you need to do, these are all raising operators. You start pushing them across. So step by step, you push them across. There is some more than, it will require more work than the previous analysis we have done, because now you have to worry about several raising operators, right? But you will see that it's not so complicated.
If you only push x alpha 2 to the highest weight, it can either.
Yeah. So in that process, you'll pick up various commutators and H2 and etc. And then you know the eigenvalues of these states when H2 acts on this, right? So you will get, and then after having finished off the x2 and the x minus 2, then you move x alpha 1. So you get rid of all of that, and then at the end you will just arrive with some number times 3030, right? 3030 suppose normalized to 1.
And you have derived this determinant condition from the fact that if we have two simultaneous homogeneous equations, if the determinant of the coefficient matrix is 0, then the solution exists. So
exactly.
You can
that is the point.
Simultaneous equations. Simultaneous equations.
Yeah, so this is the point. Because if this determinant is 0, then you see there exists a solution to this equation, n acting on, let's say, alpha and a and b, okay, equal to 0. Because if determinant is equal to 0, it means it has a 0 eigenvalue, right? In general, the determinant will have some eigenvalues, lambda i's, let's say, right? The determinant, how do you solve the equation of the eigenvalue problem? Determinant of n minus some lambda times identity matrix, that's equal to 0, right? So this is a 2 by 2. This is going to be quadratic polynomial in lambda. Left hand side will be quadratic polynomial in lambda, right? Because it's a 2 by 2. In general, if it is a n by n matrix here, if these are all n by n matrix, this is identity matrix or the same dimension. If this is an n by n matrix, this will be nth order polynomial in lambda, right? And it will have n solutions. Not necessarily real, it could be complex solutions also, right? But in this particular case, it's just a 2 by 2. So this will be quadratic in lambda. It will have 2 solutions, right? But those solutions could be, so the question is, what are these solutions, right? So is there a solution if lambda equal to 0? If there is a solution lambda, then I should be able to solve this equation, right? Lambda times a and b. I should be able to find some solution to that equation, right? In particular, for lambda equal to, if lambda equal to 0 is a solution, then I can find a solution for n a b equal to 0 0. And that will be what we in physics we call it null state. Null state meaning it has 0 norm. So this particular combination AB, where B was equal to 2A, this minus 2A, you should find that there should be a solution like this. For minus 2A, it should be 0 0. That is the exercise actually. It will require some work, but not too much. It's not as complicated as it looks like, because you have to move 3 of the raising operators across, step by step. But it's not, once you get the hang of it, it will be very quick.
We can also conclude that the beta and gamma should be conjugates of each other.
Sure. Beta and gamma, you mean?
In the matrix, N matrix.
Yeah, correct. Yeah, sure. Yeah, that's true. Yeah, correct. Yeah, so you have to compute mainly three quantities, alpha, beta, and delta.
Then the last problem, if you solve it, then the previous things are not necessary, I guess, because then you already know that they have to be linearly dependent.
They have to be linear dependent. If the determinant is 0, yeah.
So my point is that the final problem is that the previous appears to be unnecessary with the last one.
Actually, the previous one is easier to do because
Yes, it's easier to do, but
yeah,
it's unnecessary.
yeah, it's not necessary. Yeah, but it's easier, much easier to do. You see, because you have to just manipulate one raising operator. Here you have to manipulate 3 raising operators. Yeah. This kind of a problem appears in many situations. I mean, this appearance of null states.
And you can also generalize this method to any number of states, so 3 states.
Sure. But it becomes practically very difficult. So the upshot is, anyway, I mean, for the previous analysis we already know there is a, and with this exercise, in this exercise you can show that when you apply x alpha 1, again you get the same condition, that if b equal to minus 2a, the state is 0, right? So that means at the end you have only 10 states. I mean, I erased a diagram, but the diagram was, you started with the 3, 0, so you had 3 steps here, and then the picture was something like a triangle. So here 3, 4 steps, and okay, we are always going like that, no? Not alpha 3, we are not using this. So there are here, then here. So these were the 3 states. There were 2 possibilities, but actually this calculation shows actually there's only 1, right? Not 2. Unlike the adjoint representation, where there was a adjoint representation was just this part of the diagram, right? And there we had again 2 ways of getting, but you see those were independent states, H1 and H2. But in this representation, both the states are the same. There's only 1 state. So yeah, so it becomes 10-dimensional representation. Now finally, let me just do something. If I have 10 minutes, can I do 10 minutes? Because then I will stop the SU3. Then tomorrow we'll do something else.
So the homework for the tutorial this week is only this, or?
No, maybe tomorrow I will find. I mean, some of these problems can be done. I mean, it's only some of the things I've not done there. So I will just, try to look at this exercise, and tomorrow I'll tell you which ones. Now, physically, there are 2 things which one should look at. 3 times 3 bar. Tensor product. Now I'm coming to the tensor product. There are 2 things. Okay, 3 times 3, you can talk about 3 times 3 bar. You can talk about, and finally, this is also very interesting, 3 times 3 times 3. Okay. And the reason is that 3 is like quark, right? Quarks are in the fundamental representation. 3 bar are the anti-quarks. So by studying this, then one can ask, so you are kind of looking at what are the possible QQ bar states which contain 1 Q and 1 Q bar.
You were talking about flavor group
now. Or even the color group. So in the color group, the color group, if you are talking about color group, so SU3 color, then you see the physical states must all be color singlet. So then from that point of view, you are asking the question, is there any singlet in here, in here, in here? A singlet state, a one-dimensional representation. Because if it is not, then there will be no physical states which will come from there. Because the SU3 these forces are so strong that you simply cannot, they are so strong. I mean, like electromagnetism, if you take a positive and negative charge, there is an attraction between them, right? But still, I mean, they are not so strong. You can still pull them apart, no?
because the attraction actually weakens as you increase
Yeah.
the distance, but it is not in the case.
That's right. Exactly. So, okay, that's an inverse power law, the force, Coulomb law. But color force becomes so strong when you start trying to pull the quark, anti-quark separate, that that's not possible. So they form a bound state.
And the force actually increases as you increase the distance.
That's right. That's, yeah. But this you will study later. I mean, it will be much later, and in the when they discuss renormalization, that some of the coupling constant depends on the distance. And the farther you go, the coupling constant becomes stronger and stronger. So the upshot of all that is that the objects that which you can find in our lab experiments and so on, observation and so on, will be always sp3 color singlet. Singlet means neutral, no? The singlet state meaning the group doesn't do anything to that. So the important question is to find under what situations I can construct a singlet. No? So 3 with 3 bar, there will be a singlet. That is, we already saw that when you have a complex representation, its complex conjugate, I can always construct an invariant. We already found that, right? Invariant means singlet, right? When we were discussing in, I think, maybe 1 week before, 2 weeks before or something, we were discussing that, the complex conjugate representation. But quite apart from that, you can just, from the weight diagram, from the weights, you can already deduce that. And then you have a 3 times 3 times 3, and this is the fact that there are, actually it turns out that this contains, again, a singlet. Singlet meaning one-dimensional representation, plus other things. But in particular, the important point is that it contains a singlet. And that is what allows you to have protons and neutrons and so on. Because protons are made up of like 3 quarks, protons, neutrons, etc. And that is why you have, each quark is in a triplet. You take the product. So then you have, the product will, the 3 quark state will be in the tensor product or representation of that, 3 times 3 times 3.
And in the 3 cross 3 bar representation, we have gluons and mesons.
That is in the, gluons, 3 times 3 bar, correct. Not mesons, I mean, because I'm thinking of color group.
Oh, okay.
If you are talking about a flavor group, yes.
So what is physical meaning in the remaining part of the direct sum?
No, there will be lots of things, lots of other junction, because you see the dimension of this is 27, right? 3 times 3 times 3. So this 1 is 1, and then there are remaining 26, which will again split into irreducible representation. But they will not appear in the, so what kind of combination which will appear in the stable object, I mean as an object which is like baryon, proton and neutron, so it will be this part of it.
But this could be some virtual state.
Yeah,
The right hand side could be a virtual state in some interaction.
No, it's not a question of virtual state. I mean, okay, it will not appear. It will not appear in the physical spectrum. That's what I'm saying. Virtual state is a different notion. I mean, it's in the loops that internal like. Yeah. So, but I mean, here means that as physical states, this will not appear. Stable asymptotic states, it will not appear. So there's 27. So this is a few interesting questions from the point of view. And of course, then you can talk about the flavor group. In the flavor group, you can also consider another group. This is different from this group, SU3 flavor, or sometimes SU2 flavor, etc. In fact, initially, when Gell-Mann introduced SU3, it was not, Gell-Mann used SU3 was already known, but Gell-Mann used SU3 in particle physics. He was thinking in terms of flavor, because QCD was not even known at that time. I mean, people didn't even know about QCD, So he was thinking in terms of flavor group, where you had, they knew there was an up quark, down quark, and a strange quark. And even though they had different masses, and even charges, I mean, this has plus 2/3 charge, and this plus 2/3, minus 1/3, minus 1/3. These charges, electric charges. Even though these charges are different, but I mean, he just assumed. Okay, let's assume that there is a symmetry between them. So ignore electromagnetic interactions. ignore the fact that there is some mass differences. You know, strange quark is a little bit heavier than U and D. So he said, okay, let's assume for the first approximation that all of those are same mass. You know. And so you could then get some approximate symmetries. These are what is called approximate symmetry. They're not exact symmetries. Are they? Isospin, yeah. So that was this famous picture of the. I mean, initially you don't even have to think in terms of UDS. You just have the pi mesons and this octet. Okay, I think I already mentioned that. But let me just do. So can I do this or not? So there was this pi plus and pi 0, pi minus, pi 0. Sorry, what am I saying? K plus, K0 bar, K minus, and pi plus, pi minus, pi 0. So he arranged some mesons in this kind of SU3 octet system. That was the initial motivation, but of course now it has come much more fundamentally with the QCD, where the gauge interaction itself has an SU3 symmetry. This is much more fundamental. This SU3 symmetry was some kind of an approximate symmetry, not an exact symmetry. Okay, so let's quickly just do this 3 times 3. So 3. So let's just do 3 times 3. So the highest weight was 1, 0. Highest weight is 1, 0. When I take the tensor product, eigenvalues add up, right? So this has highest eigen thing is 2, 0. So remember this thing. What are the other weights? Do you remember? -1, 1, and 0, -1. Correct? And here it was 1. Sorry, this is 0, 1. No, here I'm taking the same thing. So the same 1, 0, -1, 1, and 0, -1. Okay. So I have 9 states, right? 9 states here. The highest weight would be, of course, taking the highest weights of each of them. Because if you add it up, so there will be one state with the 2, 0. That will be the highest weight state. Now the 2, 0 was what we found was 6-dimensional representation. Okay. You remember the ones we did that 2, 0. It was 6-dimensional representation. So what you do is you look at all possible weights that you can get. The nine states are here, the 9 weights, and then remove the weights that you already found in the 6. Again, maybe you can just do this as an exercise. So here, this is easy enough to do it. So you have 9 states. You list all the weights with their multiplicity, which you can do. This with that, this with that, this with that. So all the 9 states add up. The weights add up, and for each possible weight, see what is the multiplicity of the states. You can write down. Now this 2, 0 representation is a 6-dimensional representation, which you saw before. I went through that. So remove the 6 of these states from the 9. You know for sure these states must contain that, these 6 states, because that is the highest weight. You remove that, and then the question is what is left over. And you should find that this guy is this plus 3 bar. Plus 3 bar. Try that. Now, what about 3 times 3 bar? Again, 3 times 3 bar, you see this again, as far as dimensionality is concerned, is 9. What is the weight is 1, 0, and here is 0, 1. Right? So the highest weight is 1, 1. So you know this is the highest weight of adjoint representation. Right? So surely there is an adjoint representation. Okay. What is left over? There are 9. Adjoint representation is 8-dimensional. So 9 minus 8 is 1. The 1 has to be a singlet. Nothing else can happen. Right? So this should split into 8 plus 1. Plus singlet.
So we always split into all possible irreducible representation.
Yeah, just like what we did for the SU2, right? Spin J with spin J prime, J1 with J2, let's say, then highest weight is J1 plus J2. So you remove that. Then let's see what is the next highest weight and so on and so forth. It's the same procedure. So if in the process of removing so once I remove, for example here, once I remove the 6, then the 3 states are left over, right? Out of the 3 states, look for the state which had both entries non-negative, because that is what's going to be the highest weight, right? You see. So after removing the 6 states, then you look at the remaining 3 states, no? And see what is the highest weight there, which means in particular it should be non-negative integers, both. And then you will see that it should be 1, 0. After removing the 6, you should find a 1, 0 left over. And then that will give you a 3-bar representation. In a 3 cross 3 cross 3, what you will find, so again, I'm not doing it here, but try it out today, and if you have any difficulties with that, I can discuss those things tomorrow. Huh? Yeah, but just give it a try, please. So if I take 3 with 3 with 3, so each of them is 1, 0, each of them. So the highest weight is 3, 0. 3, 0 we already worked out the representation, right? That was where we had this thing that the linear independence issues arose, right? But ultimately it was a 10-dimensional representation. So you get a 10. And then, so 27 minus 10, that is 17. And you should show, for example, let's see here, 1, 0, 1, 0, 1, 0. So for example, if you look at how many ways you can get 1, 1. So you see, these are the weights. So all the 3 have the same weights, right? So if I take 2 of these guys and 1 of them. So I mean, from each of them I have to pick up 1 weight, right? From each of them and then add them. So suppose I take from here 1, 0, 1, 0 from here, and then minus 1, 1 from there. But this I could do it in 3 ways, right? I could take this from here or from there. So the multiplicity here is 3. So multiplicity of this state is 3. Of this quantum number. So this quantum number is, total quantum number is this plus that, which is 1, 1. So you see here in this tensor product, there is 1 state which has 3, 0, and 3 states which have this weights. Okay. But now in the 3, 0 representation, which is a 10-dimensional representation, there was also 1, 1, 1. If you remember that picture that we had, there was 1, 1, 1 state inside there. Only 1, because in this 10-dimensional representation, you see every weight had 1 multiplicity 1. Okay. So one of these state goes into that representation, 10-dimensional representation, which is 3, 0. Then 2 are left over. Right? So these 2 must be, this is the adjoint representation. 1, 1 is the highest weight of the adjoint representation. So you should find 2 times 2 of the 8-dimensional representation. And then what is left over? That is already 26. Total was 27. There should be a singlet. There's only 1 state left. Because this is 10 plus 8 plus 8, 26. Total here was 27. 3 times 3 times 3. 27 minus 26, then that's 1. The singlet. So 3 times 3 times 3 has a singlet. But this you knew from the tensor, I think that we discussed that. When you have a Tijk, so I'm looking at Tijk, where each I, j and k go from 1 up to 3, because we are talking about 3-dimensional representation. Right? SU3. Fundamental representation. This is 3, 3. We're looking at 3 times 3 times 3. So it has 3 index. There are 3 index because I'm taking 3 factors here. If I had taken n factors here, then this should go up to n indices. But here I'm talking about the 3 indices. And each of the index goes from 1 to 3 because we are talking about 3-dimensional representation. Okay. There is, of course, I can take a totally antisymmetric combination. Right? I can do that, totally antisymmetric combination. And that will be a singlet. Because the range of, I mean, if it's totally antisymmetric, then each of this index must be different from each other. Right? And since the indices can only be 1, 2, and 3, right? So the only possibility will be only the T1, 2, 3 will be the only thing which will survive, right? And of course the other ones, permutations of them, which is totally antisymmetric. Those are the only things will survive, right? So it will be one-dimensional. You just have to specify one of them, say T1, 2, 3. No? Then it's completely determined.
That is physical state because it's a singlet.
That is a color singlet, yeah.
No, it has to be antisymmetric because
Totally
because the quarks are fermions.
Exactly. Quarks are fermions, but also then antisymmetries, of course, once it include other quantum numbers. For example, the flavor. If there's some flavor symmetry, then you can play with various quantum numbers there. But yeah, at the end it should be totally antisymmetric. Yeah. So this is so that explains this here, and the totally symmetric one, Tijk, totally symmetric one, you can compute the dimension of this, and that should give you the 10. Because if you have 3 indices, and suppose the range of index goes up from 1 to n, let's say, okay, then it should be n times n plus 1 times n plus 2 divided by factorial 3, which is 6. Right? That will be the general formula. But now I put n equal to 3. So 3, 4, 5 divided by 6, which is 10. So that will be the 10-dimensional representation, totally symmetric. Totally antisymmetric is one-dimensional. And then those mixed, you remember we had these mixed guys, no? When 2 indices were symmetric, then those 2 should give you 8, 8, the 2 different representations. So, yeah, this is the... So please try it out and see if you have difficulties, then I can go over it tomorrow. Huh? Otherwise, I can move to a different topic. If you all have done it. And I will go through these exercises to see what you have to submit this Friday.
And since this content is not a lecture, can we refer us to any textbook or any that has them been?
I'm very bad at textbooks because I never look at textbooks, so I don't know. I can search for it and maybe I'll let you know. Has anyone looked at this reference which is given CAHN, C-A-H-N, CAHN? No? Okay, there's one very good reference which is, people like it a lot, is Georgia's book. Georgia. Georgia is written, is particularly nice because he's written for physicists. So of course he also discusses weights and roots and so on, but a huge amount of discussion is for like physics oriented. Unlike some other books you will find which is more mathematically oriented. Okay, maybe he has also gone through all these weights, because I remember he has discussed weights and roots in detail. Because those are very physical things. These weights and roots are very physical. Those are the like isospin, quantum numbers, hypercharge, all those things are there. So it's quite an important concept, important way of thinking about it. Okay. Sorry about it. I got it.